So, yes. Okay. In this second part of the lesson, I would like to present you another model that was used for the description of the properties of the solid state. This model was presented more or less 28 years after the Drude model, so in 1928. But many things happened during those years, since we have the presentation of the Pauli exclusion principle in 1925. Then we have the development of the Fermi-Dirac statistic concerning the description of the properties of the electrons in 1926. We have also the development of the Schrödinger equation formalism to describe the properties, for instance, of the electrons. Again, in 1926, if I remember correctly. So many things changed with respect to the, let's say, ideal gas picture that Drude used at the beginning of the century to describe the properties of the electrons. So the idea was to try to take these new topics, this new way to, let's say, approach the description of the microscopic elements of the materials, and to use those new information for the development of a new model. Now, I think that this model, you have already studied some parts of this model during the lessons of Struttura della Materia 1 during the third year of the bachelor degree. Since the name of the model is Sommerfeld model, maybe you didn't call that in this way, but just as free electron model, because this is the first trial to use, let's say, quantum mechanics for the description of the properties of the electrons. I say for the description of the properties of the electrons because let's say, the main difference between, the only difference between the Drude model and the Sommerfeld model is the way that was used to describe the okay, ho letto. So the only difference with the Drude model was the approach with respect to electrons. So all the hypotheses of the Drude model are used also in the Sommerfeld model. So the electrons are always free and independent, so they do not interact nor with the positive background of charge, nor with all the other electrons. So the same thing that Drude proposed, but the change here regards how do we handle electrons. So for Drude, the electrons were classical particles described by the Maxwell-Boltzmann distribution. In this case, for Sommerfeld, the electrons are quantum mechanical particles described by the Schrödinger equation and by the Fermi-Dirac statistics. So in this case, we use the Fermi-Dirac distribution to describe the properties of the electronic system. And concerning the description of a single electron, we do not consider the electron as a point particle, as a, say, a mass that moves in space according to some forces, but we describe the electron using the Schrödinger equation, and also using one of the things that Drude introduced in his model, that is the positive ground of charge is there just to maintain charge neutrality, no interaction with the electrons. So when we write down H, when we write explicitly H in the Schrödinger equation, in general H is the kinetic term plus some potential term depending on where the particle is moving. But in this case, the potential term is equal to 0 because we have no potential. Let's say we have a sort of potential because you may consider the solid to be a box. So the electron is like a particle in a box, and the box is exactly equal to the size. The size of the box is exactly equal to the size of the solid. But if we would write down the equation where we have the potential of the box, this means that we are including the surface in the model because the box has a surface. In this case, we completely neglect the surface. So we just write down the Schrödinger equation as just as the potential is 0. The contribution of the surface will be introduced thanks to the periodic boundary conditions, not through the equation of motion, or not through the Schrödinger equation. Let's say I also ask now I make this question to everybody. Supposing that you have already discussed the free electron model, I will just make a brief review of the model, evaluating the, let's say, the parameters that I will need to use in the next weeks within other models. So due to that, maybe I do not go in full detail. So I just make this proposal. If for you is fine, I keep this lineup for the presentation. But in case I say something or I evaluate something that you have not already seen during the bachelor degree, just let me know that, and I'll try to, let's say, add some details or make the calculation in more detail or give more information regarding the topic I'm presenting. May this be fine for you? Okay. So in this picture, if we suppose to solve this equation, then the solution is this. In this case, is just a plane wave, and if we want to normalize the plane wave, then we just need to divide by the volume. So the square modulus of, if we made the integral of the plane wave over the box, the square modulus is equal to 1. So the integral is equal to the volume of the box. So we just divide by the square root of the box itself. Another comment concerning why this may be a useful solution to describe the electron. This is a plane wave, and in principle, this plane wave is a wave that, let's say, has as a domain the full size of the box. So this means that if you make the square modulus of that, the probability to find an electron in any point of the box is always the same, 1 divided by the volume. So this wave function does not describe a localized electron, but just describes an electron that has a probability to be found everywhere, that can be found in principle everywhere within the solid. So how is it possible to, let's say, find an agreement between this approach, where the electron can be everywhere in the solid, and the usual approach where the electron is somewhere in the solid and is moving due to an external field or something that you are applying to the solid itself? The idea is the following. In this case, we just concentrate on the solutions, and the solutions are plane waves. In case tomorrow someone needs to, let's say, build up an actual electron that may propagate within a solid as a sort of not point particle, but as a particle that moves due to the ionic field or due to an external field, at that point, one can produce a combination of plane waves, so to build up a wave function that is not dispersed in space as a plane wave, but is localized at some point. Just to make an example, if you call phi of r the wave function of this localized electron, then this localized electron may be a combination of plane waves with G, where G is the weight of each wave vector to this combination. So G is the Fourier transform of phi of this of the wave function. So depending on the wave function you may want to use for the electron, then you obtain G through the Fourier transform, and we already know psi because we solved the problem in case the potential is equal to 0. So we know what are the different psi that we may use for this combination. So at this point, we may build up the, let's say, localized electron. This electron will be localized always in the sense that we are not able to produce a point particle. So we may not know exactly with an infinite precision the position of the electron. So will be some uncertainty in localizing the electron. But I anticipate something that we will use later. If, let's say, the size of this electron is small with respect to any wavelength of any external perturbation, then that will be fine, because if the wavelength is hundreds of nanometers and the, let's say, size of the electrons is a couple of nanometers, that is not a problem, because comparing this size with the wavelength of the perturbation, we may always consider the electron to be such as a sort of point, because the size again of the electron is negligible with respect to the wavelength of the perturbation. So from now on, I will always use plane waves. But again, in case we need to localize the electron, we use the Fourier transform and we build up a new wave function as a linear combination of plane waves. So to build up any possible wave function for the actual electron in the solid. And due to the fact that here you have no potential, so V is equal to 0, this means that the Schrödinger problem is invariant under translations. So the fact that we have invariance under translation means that the momentum is a conserved quantity. So the wave function, in this case the plane wave, will be also an eigenfunction of the momentum operator. So the momentum operator P is minus I h bar nabla, and the if we apply P to a plane wave, what we find is that this is equal to h bar k. So sorry. So that is equal to h bar k. So the momentum of the plane wave is proportional to the wave vector of the plane itself. And that wave vector or momentum can be considered to be, again, a constant of motion. And h bar k, so, will be related to the velocity of the electron. So what we know is that both the energy that we evaluate in a while and momentum are two parameters that are always constant as the electron moves freely within the solid. Concerning K, for the moment, K, in principle, may be a continuous parameter. It's just a wave vector. So in principle, any vector could be fine within that wave function. But this is not true if we take into consideration the periodic boundary conditions. So what, let's say, why do we need to use periodic boundary conditions? The fact that we use periodic conditions is due to the fact that if we consider, again, the solid is a box. If we, just to make an example, suppose that this wave, if you're supposed to have a wire of a guitar and you want to see the waves that can be produced by this wire of the guitar, if you suppose that the box is closed, that means that I keep fixed the two borders of the wire of the guitar. This means that the amplitude here will be always 0. So what I find is just a stationary wave within the wire. If I want the possibility to have not a stationary electron, but a propagating electron, that I do not have to look for stationary waves, but I have to look for waves that are able to propagate within the solid. So due to that, the borders of the solid are not considered to be walls where the electron may not, let's say, is forced to have an amplitude equal to 0. So due to that, to avoid this problem, so to obtain stationary waves, the idea is to say that if this is, let's say, one dimension of the box, so this is side, let's say, along x, this is the length of the solid along the x direction, what is generally asked is that the value of the wave function here on one side of the solid, or on one side of this box, is equal to the value of the wave function at the other side. So if you look at what is the effect of that from the geometrical point of view, instead of having a wire, you have a circle, because the last point of the wire is equal to the first point of the wire itself. So you transform a line into a circle. Or if you have a two-dimensional picture, you have a square, let's say. If you make the two opposite sides to coincide, you produce a torus. So in this case, you transform the surface of the solid from something that prevents the electron from, let's say, what actually happens, moving through the surface. So instead of considering that a sort of wall where the amplitude goes to 0, you just join the end of the solid with the beginning of that. In this way, all the waves that go through the solid has the opportunity to infinitely propagate through the solid in any direction. So looking at this picture, anything exiting on one side comes back from the other side. So there is the opportunity of propagation. This doesn't happen since the relaxation time prevents this from actually being observed. But from the mathematical point of view, this is done just to, again, prevent the formation of stationary waves. So if we apply this condition to the plane wave, we have that psi of k in 0 is equal to 1 divided by the square root of the volume. And this should be also equal to e to the minus I. I write kx because I'm just considering one of the three directions of the solid, times Lx, so the length of the solid, divided by the square root of the volume. So due to that, I have that kx times Lx has to be equal to 2 pi nx, where nx is an integer that may be positive or negative. And then we have 2 pi. So kx is 2 pi nx divided by Lx. Due to this condition, k is no more a continuous variable, as k can assume only discrete values, and those values are related to 2 pi divided by Lx times an integer number. So from now on, k will not, let's say, cannot be really considered to be a continuous parameter. What you find here for kx is equal to what you find for ky and kz. So what we have is at the end is that the k vector of the electron is equal to 2 pi nx divided by Lx, 2 pi ny divided by Ly, and 2 pi nz divided by Lz. If you now consider the space of the wave vectors. So in this way, all possible values of k belong to this space where we describe those vectors. And if you notice here, the k vectors describe a lattice in this space. And the lattice is a cubic lattice if Lx, Ly, and Lz are equal with each other, or any case is a space resembling a sort of cubic symmetry, because again, you have discrete points equally spaced along x, along y, and along z. So if I make a short plot of that, we have kx, ky, and kz is in the orthogonal direction, and all the possible points, that means all possible k values, are found on this lattice. And the spacing of the lattice is 2 pi over Lx in the x direction, 2 pi over Ly in the y direction, and 2 pi divided by Lz in the z direction. So let's say when you consider the problem, the solution of the Schrödinger equation for instance, hydrogen, what you found was that hydrogen, the electron in that case has a wave function that can be described by different quantum numbers. You had the principal quantum number, then so you have some discrete parameters that allow you to distinguish all the wave functions of the electron in a given situation. In this situation, so free electron within this box, the equivalent of those quantum numbers is k. So k, with these three components, is a sort of quantum number that identifies in a precise way one single electronic wave function. So if you fix an x, an y, and an z, you choose one point in this lattice. That point corresponds to a wave vector. That wave vector corresponds to a wave function. So we have a one-to-one correspondence between points in this space and electronic wave functions in, let's say, real space. So this is the wave vector. The wave vector space, where we have all possible wave vectors that can be used for the electronic wave functions, and each point of this space corresponds to one electronic wave function, or in other words, one electronic level. Because if you consider the atomic picture, if you fix all the quantum numbers, you fix the wave function of one level. Then there is an additional choice that is the choice of the electronic spin, of the spin of the electron. So each of those points is a level that may host two electrons, one with spin up and one with spin down. So to each point in the wave vector space correspond one wave function that can be used for two electrons, one electron with spin up and one electron with spin down. So this is a consequence of, this picture again is a consequence of the introduction of the Pauli exclusion principle that tells you that you have not the opportunity to observe two electrons with the same quantum numbers. So one point of this in this space fixes not all the quantum numbers because you have the variability of the spin, and then you fix the spin at the end when you fix the spin, when you choose the spin of the electron that you want to describe or you want to investigate. So from now on, I will always use the two pictures in parallel. These two pictures are the electron in real space that is described through the use of the electronic wave function. So the wave function depends on the R position, so we are working in the real space, and wave vector space that is the space of the wave vectors. To use a term that I think you have already seen, this will then become the space where we have the reciprocal lattice. So this will be the same space where the reciprocal lattice will appear when we will consider the fact that the ions are not, let's say, when we will consider that the ions occupy fixed positions. So, but for the moment, we just call that wave vector space. An important property of the wave vector space is the following. If you consider all these points, again, they are equally spaced. So this means that there is the opportunity to build up something similar to the elementary cell that you maybe have seen when discussing about the Bravais lattice or also on the reciprocal lattice. So a volume in space that may be replicated from point to point of this lattice, so to fill all the space without leaving voids or without overlaps. And in this case, due to the symmetry of the lattice, we may use as this cell, as this volume, a square box in case Lx and Ly and Z are equal with each other, or a rectangular box that can be translated in space, so to fill all the space without leaving voids and without overlaps. Now the question is, what is the volume of that box? The volume of that box, since we are working in the wave vector space, is a volume in the wave vector space. So it's not in a expressed in cubic meter, but in meters to the -3. So the volume is equal to 2 pi over Lx times 2 pi over Ly times 2 pi over Lz. The product of the three L's is the volume of the solid, so this is equal to 2 pi to the power of 3 divided by the volume of the solid. An important thing, an important meaning of that is the following. If you consider that picture, so each point is surrounded by this volume, and in that volume only one point is found. You may consider that volume to be the volume of the cell, so of this primitive cell, let's say, that you use for this lattice, but you may also consider that to be the volume of one level. So there is a one-to-one correspondence between cell and level, because each level is surrounded by just one cell, and each cell contains just one level, just one point. So I will often use this quantity as an estimate, or no, not an estimate, but as the actual size of the volume of one level. And please consider that volume of one level means one level corresponds to one point in this space. One point in that space corresponds to one cell that surrounds that point. The volume of that cell is always the same, that is 2 pi to the power of 3 divided by the volume of the solid. Due to that, we have a one-to-one correspondence between level and cell. So I use this one-to-one correspondence to say that the volume of that cell is the volume of one level. So in this sense, I will use the expression volume of one level in during the calculations. Okay, so this is the geometrical structure that we need to handle all the levels and to organize the occupancy of the levels as soon as we introduce the actual electrons in the system. I just need one more detail, and then we can start to fill the levels with the electrons. And the other detail is the energy. So now we have to find a correspondence between energy and level. And due to that Schrödinger equation, and to the fact that the wave function of that Schrödinger equation is a plane wave, what we find is that the energy is h bar squared times k squared divided by twice the electronic mass. And as h bar k is the electronic momentum, you may write this also as p squared divided by 2m, as you find in classical mechanics. So to stress the fact that the energy depends on the wave vector, I write E of k. And please consider that the energy depends on the wave vector just on the square modulus. So the two levels having the same modulus of the wave vector but different direction have exactly the same energy. So the energy is the same over, if you choose a sphere, all the levels over the surface of that sphere have exactly the same value for the energy. At this point, we have everything we need to fill the levels and see what happens. And in this case, what happens is that as soon as you count your electrons, and the number of electrons or the electronic density is the same that was used by Drude, since at the moment there is not a different way to estimate the electronic density. So the electronic density is always n, that can be calculated according to the Drude mechanism. So same method for calculation. So if we know the number of electrons that we need to host in this system, we start by filling the levels with low energy. Then as soon as those levels are filled, we use levels with higher energy, and so on and so on and so on. So the final point is that since all the levels that lie on the surface of a sphere have exactly the same energy, the symmetry of the levels in this space will be a spherical one, because on a sphere, all the levels on the surface have the same energy. So you fill this system by filling spheres whose radius is always larger as soon as you continue to inject electrons into the system. So what you end up with is just that at the end, all the levels that are occupied levels are levels that in this space produce a sphere. So the interior of the sphere is made by occupied levels what is out of the sphere is, and out of the sphere you find just empty levels. And the highest possible level that is occupied is what you is the Fermi level. So in this case, the point is to evaluate the maximum possible wave vector that has to be used to host all the electrons in the system. And due to the fact that this is the Fermi surface, that vector is called Fermi wave vector. So the question is, the point is, how may we estimate Kf? If this is a sphere, the volume of the sphere is 4 divided by 3 pi Kf to the power of 3. How many levels can be included in that sphere? We just divide the full volume of the sphere by the volume of one level. And the volume of one level is 2 pi to the power of 3 divided by the volume of the sample, of the solid. Each level may host 2 electrons, one spin up and the other one spin down. So if this is the number of levels in the sphere, we have to multiply that by 2. So we have the total number of electrons that be included in the sphere. And that should be equal to the number of electrons. So this, we have a volume here at the denominator. This volume here can be taken on the other side of the equation. So that becomes n electron divided by V. So that is the electronic density. So this equation allows us to find the connection between Kf and the electronic density. So we have 8 divided by 3 pi Kf to the power of 3 divided by 8 pi to the power of 3, that is equal to the electronic density. We may simplify 8 and pi, and what we have is that Kf to the power of 3 is 3 pi squared electronic density. And yeah, so at this point we know the size of the sphere. Please keep in mind, since that will be important later, that the size of the sphere is related to the electronic density. So the larger the density, the larger the sphere, the smaller the density, the smaller the sphere. And if we try to, let's try to find just a rough estimate of Kf, just to fix the magnitude, the order of magnitude of that vector. Kf is equal to 3 pi to the power of 2, and everything is to the power of 1/3, times electronic density to the power of 1/3. 3 pi is more or less 3. So in the parentheses, we have 3 to the power of 3, more or less. So at the end, the square root, the cubic root of 3 pi to the power of 2 is more or less 3. So this is nearly 3. Then the density is of the order of 10 to the 28. It's larger than that, but the order of magnitude is 10 to the 28 electrons per cubic meter. So the cubic root is equal to the cubic root of, I just write 10 to the 28 as 10 times 10 to the 27, just to make the calculation simple. So this is 3 times, the cubic root of 10 is more or less 2. And the cubic root of 10 to the 27 is 10 to the 9. So this is something that is of the order of 6 times 10 to the power of 9 meters to the -1. Why did I want to evaluate Kf? Kf is a vector of a sphere that lies in a space where we have a lattice describing all the possible electronic levels. What is the lattice spacing? The lattice spacing is of the order of 2 pi divided by L, Lx or Ly. So the spacing of this lattice is of the order, let's say, of 2 pi divided by the size of the solid. If the size of the solid, just to fix a number, say the size of the solid is a macroscopic parameter, millimeters, centimeters. If we just fix, for instance, 1 millimeter, 1 millimeter, this is 2 pi divided by 10 to the minus 3 meters. So this is more or less 6 times 10 to the power of 3 meters to the minus 1. So the main conclusion is that the size of the sphere is 6 orders of magnitude larger than the lattice spacing. So at this point, I have, for instance, the energy. If you consider the energy in principle is a discrete parameter because K is not a continuous parameter, but has just discrete components. But the energy varies across all the levels from K equal to 0 to K equal to Kf. So you have a huge range of variation. And this range of variation, in particular Kf, is again larger and larger with respect to the lattice spacing. So the main conclusion is, yes, the spacing is discrete, the lattice is discrete, but all the quantities that I will evaluate for the lattice can be considered to be continuous quantities. That is why I wrote in the description of the energy, not EK label, but E of K as if K was a continuous parameter. So from now on, I will use K as a continuous parameter because the relationship between Kf and K is the one that we have just seen. So again, all the parameters that I will use from now on to make an integral or whatever are always parameters that are supposed to be continuous variables, because let's say the discrete nature of those variables disappear in front of such a huge range of variation of all the parameters that can be used to describe the motion of the electron. So K will be considered to be a continuous parameter. And yeah, this is quite important when we, in particular, want to sum quantities. For instance, if we want the total energy of the electrons, we have to sum the energy of all the electrons. In that case, this fact can be useful to transform the summation into an integral, because we may consider again K to be a continuous parameter. And before making any calculation, I just want to introduce a parameter that I will use also the next days. And I think you have already used that. In this picture, so if you consider this picture, what is the level density? The density of the levels in that space is uniform because all the space, because the volume of one level is always the same. So given given a fixed volume in that space, the number of levels you have there depends just on the ratio between the volume you consider and the volume of one level. So the density of levels is uniform in space, in the lattice, in this wave vector space. But many times we will also have to consider the energy of the levels. And in this picture, the energy is the same if you consider, for instance, all the levels that are found in this small annulus, I think, questa, come si chiama? Non mi viene in mente il termine, cioè ha un nome quello spazio lì, ma al momento non mi viene in mente il termine tecnico. Anyway, the level, due to the fact that the energy of the levels depends on the square modulus of the wave vector, all the vectors belonging to these small regions here between at the surface of this sphere will have nearly the same energy. So it's interesting to evaluate not just the density of levels with respect to K that we have already evaluated and is constant, but the density of levels with respect to the energy. I think you have already seen that. Is that correct? Do you remember that? Okay, but the calculation is quite short, so I was going to do that. So let's suppose that we are, let's suppose we decide to sum something. We want to evaluate the quantity over the electronic system. For the moment, I just, oh, sorry. Okay. Yeah, so let's just suppose F is an arbitrary quantity, whatever, something that we will need tomorrow. And what we suppose is that quantity depends on the wave vector just through the energy. So F depends on K, but the dependence is just through the energy, not through K in itself, just through the energy. At this point, what we need to do is, let's say, not we need to do, but what we are allowed to do is to transform this summation into an integral, thanks to the fact that the spacing between one level and the next is very, very small with respect to the volume of integration, let's say. So how can we make that kind of transformation? We may use a spherical not spherical. For the moment, we just use the coordinate volume using Cartesian coordinates, x, y, and z. Then we have this d3k represents a small volume in this space where we have the wave vectors. How many levels are found in that volume? We have to divide d3k by the volume of one level, that is 2 pi to the power of 3 divided by the volume. Then we have the quantity that we want to sum up, want to evaluate. Okay. At this point, we may switch from Cartesian coordinates to spherical coordinates due to the fact that the energy has a spherical symmetry. So this is volume divided by 2 pi to the power of 3. Then the volume element in spherical coordinates is k squared sin theta d theta the phi, so the two angles that allows us to describe all the sphere. And then we have again F of energy of K. Due to the fact that the energy has a spherical symmetry, so the energy does not depend on the two angular variables, we may integrate over the two angular variables. And the integral of that is 4 pi, so is the surface of the sphere. So this is 4 pi. So we are just left with the integral over the modulus of K. We have volume divided by 2 pi to the power of 3. Sorry, I forgot 4 pi. Then we have k squared times f e of k dk. Integration. For the moment, I suppose that I want to sum up only over the levels within the sphere. So k ranges from 0 up to kf, so the maximum possible wave vector. Yeah. So I have volume divided by 2 pi to the power of 2, because I simplified 4 pi with 8 pi to the power of 3. Then I may change variables. So I may switch from the wave vector modulus to energy, due to the fact that the energy is h bar squared k squared divided by 2m. So at this point, I change the variable of integration from k to energy. And I also have to consider that for what concerns replacing dk with dE, dE is equal to h bar to the power of 2, 2k dk divided by 2m. So if I write k squared as k times k, then I have f e of k dk. Then k dk, this term here, is equal to the product of these two. So in place of k and dk, I will substitute dE times, so k dk is equal to dE times m divided by h bar squared. So this is equal to volume divided by 2 pi to the power of 2 integral. F is now f of e, because I assume that that f depending on k only through the energy. Then I have k dk, that is m divided by h bar squared times dE. And also I have k, and I obtain k from this equation. So k is 2m divided by h bar squared times the energy to the power of 1/2. So I have 2m divided by h bar squared times e to the power of 1/2. Limits of integration. 0 kf corresponds to 0 Fermi energy. At this point, I need an additional substitution, so to reach the final point, and the substitution regards this pi squared, because we have just seen that 3 pi squared n is equal to kf to the power of 3. So pi squared is equal to kf to the power of 3 divided by 3n. So I make this substitution into the calculation. So I end up with v divided by 2 times kf to the power of 3 times 3 times the electronic density integral from 0 to ef, f of v, m h bar squared, and I have 2m divided by h bar squared. I just separate I break the parentheses into two parentheses, one with just 2m divided by h bar squared, the other one with just e, and then I make the square root. Now, if you note, this kf to the power of 3 can be written as kf squared times kf. If you take this kf here, I just now I write everything. I will bring 1 kf here and 1 kf within the parentheses. So 1 kf is here, and if I multiply and divide by 2, this is 1 divided by EF. This is 1 over EF, because it's just the opposite of of the expression of the energy. And then if you look also at the first parenthesis, we have 2m divided by h bar square kf squared, because if I take kf within the parentheses, I have kf squared within the parentheses. And this is again 1 divided by EF. And then I have the energy to the power of 1/2. Yeah, if you don't mind, just since it's about 11:30, and due to the fact that from now on you have just rearrangement of the terms, if you consider this, you end up with the final solution where this integral is equal to 0 EF of f of E g of E dE, and I use this integral to define g of E. So f of E is here, dE is here, everything else is grouped into g of E, and g of E is equal to 3 divided by 2 electronic density divided by Fermi energy times energy divided by Fermi energy to the power of 1/2. Just try to check that. If you have some questions or comments tomorrow, some comments, I will go on with the other details of the calculation tomorrow. The idea is that the electronic density as a function of the energy is proportional to the energy to the power of 1/2. So what we have here is that if we plot g of E as a function of the energy, we have the square root of the energy. So the number of levels per unit volume and per unit energy increases as you increase the energy. And that is due to the fact that if you consider a small sphere, then the number of levels will be proportional to the surface of the sphere, and the surface of the sphere increases as the radius of the sphere increases. So the larger the energy, the larger the sphere, the larger the number of volume of levels that you have corresponding to the specific value of the energy. So that's why the energy density expressed as a function of energy increases with the value of the energy. Okay, if you have short questions or short comments, we may discuss those now. Otherwise, I may discuss about those tomorrow morning as soon as I start the lesson of tomorrow. But please, if you have some details or something short now, I may answer to that. Okay, so now I stop the presentation. And yeah,